Okay, in the last lecture, we were computing the slope for the cardioid, and what we have found is this, that I just recall, that dy by dx, what we have found is that it is cos theta into 1 plus 2 sin theta divided by 1 plus sin theta 1 minus 2 sin theta. Here we have not worried about when we are dividing it whether the denominator is 0 and so on and so forth. So, this is what we can, this is a very formal calculation. However, so what we can say is that whenever this is valid, this expression when dx by d theta is not equal to 0, then only we can do this computation. So, now once we have done this computation, what we have found is that dy by dx, the slope when the angle is pi by 3. So, this is going to be minus of 1. So, this is as you can see that this slope is going to be minus of 1, which means this angle is pi by 4. So, therefore, the slope this is going to. So, this is what the slope is going to look like. Okay, so, now let us see some other points. So, as we can see, so we have what we have got, that we can go to back to this slide here, and as you see dy by d theta, this is going to be equal to cos theta 1 plus 2 sin theta. So, now dy by d theta is equal to 0 if theta is equal to, because 1 plus 2 sin theta can never be can be 0. So, yes. So, this is pi by 2, this is going to be equal to 0, and then this is 3 pi by 2, then this is again going to be 0, and in this case if it is going to be, let us say 7 pi by 6, then this is going to be minus of half. So, into 2 negative 1. So, this is also 0. So, this is 7 pi by 6. Also on at 11 pi by 6, sin theta is going to be minus 1 half. Therefore, this is also going to give you 0. Similarly, therefore, what do I get? I get that on these points at theta equal to pi by 2, and I have got this is pi by 2 is 2, 2 0. So, this I am going to get a horizontal slope here. Now, when theta is equal to 3 pi by 2, this is I am going, I do not know what it is. So, let us wait for this. Now, at theta equal to pi by 2, I have dx by d theta, this is equal to 1 plus sin theta into 1 minus 2 sin theta. So, this theta equal to pi by 2, this is not equal to 0. This is not equal to 0, therefore, I am going to get a horizontal. Theta equal to 3 pi by 2, 3 pi by 2, this is 2, then this is 3 pi by 2, this is also 3 pi by 2, this is going 1 plus sin theta is equal to 0. Therefore, dx by, so we are not talking about 3 pi by 2. Now, if you look at 7 pi by 6, then dx by d theta is not equal to 0. So, with the 7 pi by 6, this is at this point. So, we are going to get a horizontal, and at 11 pi by 6, what we are going to get is again here a horizontal tangent. So, we can say that the horizontal tangent tangent at pi by 2, 7 pi by 6 and 11 pi by 6. Actually, we can write down the points for which this is going to happen. So, you just plug in the point. So, this is, you can more precisely write 2 comma pi by 2, and this, if we calculate, this is 1/2 7 pi by 6, and for 11 pi by 6 we are going to get 1 by 2 11 pi by 6. So, we have got the horizontal tangent. So, now in this, let us try to see where dx by d theta is equal to 0. Now, dx by d theta is equal to, going to be equal to 0 if x is equal to 3 pi by 2 and pi by 6 and 5 pi by 6. You see, accepting this point pi by 2, 3 pi by 2, pi by 6, 5 pi by 6, 7 pi by 6, 11 pi by 6, we have no issue that I mean dx by d theta is not equal to 0 and dy by d theta is not equal to 0. So, for this we can replace the pi by 3 and plug in the value of the theta, and we get a concrete expression. Only problematic points are here. So, now we have handled when dy by d theta is equal to 0 except 3 pi by 2, because dx by d theta is also equal to 0. So, apart from that, when dy by d theta is not equal to 0 at pi by 6 and 5 pi by 6. So, what it is going to, dy by d theta is not 0, and at the denominator you are going to get the 0. So, what do you get in those cases? In those cases, what you are going to get is the vertical tangent, right. So, vertical tangent at the point pi by 6, then this, if we calculate, plug in the value, this is 3 by 2 and r is, and then 5 pi by 6, this is also 3 by 2. So, vertical tangent is going to be here at this. So, this is the vertical tangent, and 5 pi by 6 is here at this point. So, you will get a vertical tangent. So, now we are only left with the point, this is the 3 pi by 2. So, now this is in the form of 0 by 0, because dy by d theta is also at 3 pi by 2 is equal to 0, and dx by d theta at 3 pi by 2 is also equal to 0. So, now how do we proceed with this? Obviously, what we need to find in order to get dy by dx. So, we must need to find the limit. So, now let us take, that means we want to consider, let us say theta goes to 3 pi by 2 minus from the negative side, and then we will find 3 pi by 2 from the positive side. So, so now this is going to be, we want to get dy by dx. So, this means this is limit theta goes to 3 pi by 2 minus, and this is nothing but cos theta 1 plus sin 2 sin theta divided by 1 plus sin theta into 1 minus 2 sin theta. Okay. So, cos 3 pi by 2 is 0, 1 sin 3 pi by 2 is negative 1. So, now if it is negative 1, these two are not creating problem. So, let me take 1 plus 2 sin theta divided by 1 minus 2 sin theta, and then this is cos theta divided by 1 plus sin theta. This, the first is not a problematic one, the second is a problematic one. So, let us take the first out. What we get is that this is minus of 1 by 3, because this is equal to 1, and so what we get is this. Okay. And then limit theta goes to 3 pi by 2 minus cos theta derivative. So, now it is 0 by 0 form, 3 pi by sin 3 pi by 2 is negative 1. So, this is 0 by 0 form. So, we can apply the L'Hopital rule. So, which is equal to minus of sin theta divided by cos theta. So, this term, this goes to infinity with a negative sign. So, this is equal to infinity. So, because of symmetry, limit theta goes to 3 pi by 2 plus dy by dx, this also we get at infinity. So, which means we are going to get a vertical tangent. So, a vertical tangent at 0, at the point 0 0 or 3 pi by 2, right. So, now all the pictures are drawn. So, here we have the vertical tangent here and here the horizontal tangent. So, this is what is of the cardioid. Okay. So, once we have done, so naturally the next thing we would like to look for that the area bounded by the curve which is given to us in polar coordinate. So, let us we know that we have to find the area, we have a prescription of Riemann. So, what is that prescription? Now, the function is defined through a variable x, y equal to f of x. Now, to find the area, so we divide, partition the domain of the function in our interval case. So, we take the partition, then we take the Riemann sum, and then with the we approximate the area through the Riemann sum, that is, and we take the finer and finer partition. So, we get it in terms of the integral. That is how we have derived the area under the curve. Exactly, we are going to have the similar approach here. So, here what it is given to us? Here it is given to us is that r equal to f of theta. So, now look at in the Riemann case. Riemann case, when we are approximating getting a partition, so what we are going to get are rectangles. So, it was easier for us to compute the area of the rectangles and then we are taking the sum. Let us see what we are going to get here. So, pictorially, suppose we have a function which is given like this. We want to find the area under this. So, which means so now this is this point, this line is theta equal to alpha, this is theta is equal to beta. So, now what we are going to do is that we need to make a partition of this entire thing. So, let us make a partition of this. So, now here obviously we are not going to, we want to get the area of each of these sections. So, how we are going to find the area of each of this section? There is no rectangle inside it, but you know we can consider this as a, if we look at this. So, this is the area we are looking at in some way. So, let us say with a small one, this is looking like this. So, we can approximate this by what is the most natural thing. If I make this as a circle, part of the bigger circle, let us say this circle, then I can find the area of the circle, and depending on the theta I can find the area of that section, and that is precisely what we are going to do. Okay. So, now we have r is equal to f of theta. Now, consider a partition P, which is alpha is equal to theta 0 less than theta 1 less than theta n, which is equal to beta. So, now the what is the radius? Radius is nothing but this is f of theta. If I have this is theta, then this is nothing but f of alpha, this is f of theta 1, like this. So, the radius is going to be your f of theta, that for the area of the entire circle is going to be pi f of theta square. So, now this is nothing but theta 1 minus theta 0, or theta I minus theta I minus of 1 is the angle. This angle is theta I minus theta I minus of 1. So, now what will be the area of this portion? So, the area of this sector where theta belongs to theta I minus of 1 to theta I, this is can be approximated by so this is pi f of theta I star, this is the area of the circle, and then you have theta I minus theta I minus of 1 divided by 2 pi, because this entire is the angle is 2 pi. So, this comes out to be theta I minus theta I minus of 1 f of theta I some star, where theta I star belongs to anything between this. So far so good. Then we take the Riemann sum. So, this is a factor of half is there because 2 pi. So, now the Riemann sum is given by I from 1 to n 1 by 2 theta I minus of 1 f of theta I star square. So, this in our notation of delta we write that this is half I equal to 1 to n delta of theta I f of theta I. star square. So, now if we take the limit, this Riemann sum, this converges to half, then you have alpha to beta is your variable, theta is varying from alpha to beta, and this is f of theta square d theta. This is what is the area. So, area is equal to 1 by 2 alpha to beta f of theta square of d theta. This is what. Now, we have derived a cute formula for the area if our curve is given in terms of polar coordinate. So, now let us do some example. So, find the area enclosed by 4-leaved curve r is equal to cos 2 theta. So, just recall we have sketched the curve. So, this is going to be this, and then from pi by 2 to pi is this, pi to 3 pi by 2 is this, 3 pi by 2 to pi is this, and this is what. So, we will find out the area. As you can see, this curve is symmetry, although I have not drawn it properly, nevertheless this is symmetry. So, if we can find this area of this region and we multiply it by 8 times, then we are going to get the entire area. So, or we get it for the one loop and then we try to find out the area if we find, and then we multiply it 4 times. This is as we had done. So, now here f of theta is equal to what? Cos 2 theta. Now, for this, if we want to do for one loop, let us do it for this loop, then this is going to be 0 to pi by 4. So, the area of let us call this loop as L1, this is equal to 0 to pi by 4, and then 1/2 of f of theta square is cos square 2 theta d theta. So, this is equal to 1 by 2, 0 to pi by 4, cos square 2 theta is 1 plus cos 4 theta d theta. This is equal to 1/2 of 0 to pi is the first one is theta, and pi by 4 minus this is pi by 4. And then cos theta is sin 4 theta by 4, this is 0 to pi by 4. So, this is going to be, this is I made a simple mistake here. This is 1 by 2, 2 cos square 2 theta is equal to 1 plus 4. So, now this instead of 1 by 2, I have got 1 by 4 here. So, this is nothing but pi by 8, pi by 16. So, the total area is equal to 8 into pi by 2, pi by 16, which is equal to pi by 2. So, the area of this enclosed area of r cos 2 theta is going to be pi by 2. Okay. So, now let us do another example. So, example 2, find the area of the region that lies inside r equal to 3 sin theta and outside cardioid r equal to 1 plus sin theta. So, this is what is going to be. So, if we look at the curve r equal to 3 sin theta, so which means what is the curve what you are going to get? This is x is equal to 3 sin theta into cos theta, which is equal to 3 by 2 sin 2 theta, y is equal to 3 sin theta into sin theta, which is equal to 3 sin square theta, which is equal to 3 by 2 into 2 sin square theta. 2 sin square theta is equal to 1 minus cos 2 theta, 1 minus cos 2 theta. Therefore, this is going to be the circle x square plus y minus 3 by 2 whole square. This is equal to 9 by 4, which is 3 by 2 whole square. So, this curve is going to be y equal to 3 by 2, 0, 3 by 2 center and then 3 by 2 radius. So, this is nothing but the circle with this. Now, what we know, we have sketched the cardioid. So, which is going to be 3 by 2, this is 3 by 2. So, this is 3. So, this the cardioid is going to be something like this. So, we want to find the area of the region that lies inside this and outside this. That means, we are interested in finding the area of this. As before, what we need to do is that we need to find where they meet. So, now this is 3 sin theta, this is equal to 1 plus sin theta. So, this implies that 2 sin theta is equal to 1, this will imply that sin theta is equal to 1 half. So, theta is equal to pi by 6 and pi by 6. This is the region what one on the first quadrant and on in the second quadrant. Therefore, the area is going to be, so the area this is going to be 1 by 2, we have pi by 6 to 5 pi by 6 and f theta square, f theta is given to be 9. Here f theta is this minus of this, f theta minus g theta, f theta square is 9 sin square theta minus 1 plus sin theta whole square d theta. So, if we do the simple calculation, so this is going to be, this is simply you just calculate with your trigonometric substitution and what you are going to get is pi. That is what is the example of the area. So, as we know that f x and g x, then the area covered by f x and g x is, if f of x is greater or equal to g x, then the area is f x minus g x area. So, this is what is, this is exactly the same thing what we have done, and we get that it is pi. So, thank you. We will continue with the polar coordinates in the next lecture. Thanks.